In this video, let's talk a little bit about the difference between exponential and linear growth. So let's begin with something that we know to be linear. So how about y equals 2x? So again, when we think about linear functions, right, we think of y equals or f of x equals mx plus b. That's kind of the form we've gotten familiar with through other algebra classes. And the neat thing about linear functions is the slope is constant. So of course, there are some practical applications, but many other real life things require functions with non-constant slopes. So if I were to graph that, we know again it's a straight line. Because the y-intercept is 0, I'll just go ahead and plot some points. So 0, 0, then the slope of 2, right? The slope tells us how to move from there. And the slope is understood to be this value in front of x. And I always like to think about slope as a fraction because slope has a rise and a run. So from the y-intercept, I'm going to rise by 2, run by 1, put down another point, and I can continue that same behavior indefinitely, really in both directions from the y-intercept. So I can keep going up by 2, over by 1, up by 2, over by 1. I'll just go one more, up by 2, over by 1. So those points obviously connect and form a straight line. I could also go down by 2, left by 1 to get moving to the left of the y-intercept. So let's just connect those points. I'll do my best here. And that will be a linear function. So we're familiar with linear models from the past, right? And then I'd like to just immediately contrast that with exponential, which is what we've been studying more recently. So let me fill in the table just for what it's worth as well. We just dove into the graph, but a lot of you are familiar with organizing your points in a table and then graphing from there. So I'm kind of working it backwards. When x is -1, the y value we found there was -2. We had 0, 0 as the intercept. We had 1, 2. We had 2, 4. And then we had 3, 6. And then you can see we went a little further and even got 4, 8 there. Okay. Great, so that's linear growth, right, where the slope is the same from one point to the next. Now let's compare that right away with exponential. Let's say I have y equals 2 to the power of x. So just a small change in the location of the x, it's now the exponent on 2 rather than the multiple with 2 as we saw in the linear function. And let's just plot some points for that as well. I'm going to use the same inputs I just showed in the linear table. And let's find the outputs together. I'll find the outputs first for this one, and then we'll go over to the graph. So I need to take each x and insert it as the exponent. So 2 to the power of -1 is the same as 1 over 2 to the first, and 2 to the first is just 2. So there's a little bit of side work to justify 1/2 as the output when x is -1. When we take 2 to the power of 0, anything to the power of 0 is just 1. So the output corresponding with x equals 0 is 1. The next couple are a little bit more straightforward. 2 to the first power is just 2. 2 squared, 2 times 2 would be 4. And 2 cubed, 2 times 2 times 2 would give us 8. Okay, so let's go ahead and plot those points from the table and then we'll make a couple comments and wrap this up. But I just think it may help to look at these two models side by side to understand really their differences, I guess. So when x is -1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2, so we shared that point. When x is 2, y is 4. When x is 3, y is 8. And if we kept going, I'd get off my graph very quickly. That's the thing about exponential growth. My next point would be, 4, 16. So it grows very quickly. So we have a little piece coming up right through here. I'll just connect these points best we can here. So in purple, we're showing the exponential. Let me just write this out again at every stage to just keep drilling home this difference. So exponential versus what we've spent so much of our previous math history working with, which was linear. So looking at these side by side, we notice a couple similarities. Both have domains of all real numbers, so that's kind of neat. The ranges are different. For the linear model, it's all real numbers, but for the exponential, it's actually just 0 to infinity. What else do we notice? The slope of the exponential is not constant, right? So that's kind of one important thing I wanted to make sure we leave feeling good on. So from this point at 0, 1 to this point at 1, 2, if I tried to approach it from a linear perspective, you would say, okay, I went up by 1 unit and then I went over by 1 unit. But if I try to apply that slope from one point to the next again, up 1 over 1, it doesn't work, right? Because the slope is actually changing. From this point at 1, 2 to the point at 2, 4, then I'm going up 2 over by 1. And then I'm going up by 4 and then over by 1. So the slope of the exponential is changing from one point to the next. And that is definitely how it's different than linear, where if I drew the little steps for the linear model, the steps would all be the same size, right? So that's the thing. So if you want to walk up a staircase, you do want all the stairs to have the same slope from one stair to the next, otherwise you'll trip and fall. But for exponential, that's not the case. So anyways, the reason I wanted to talk through all of this was you have a homework question that's going to ask you to investigate a little bit about this difference. So maybe now's a good time to bring that question in and we can look at it together. Let's see, I think I've got it ready to roll here. So we need to determine from a table if a function is linear, exponential, or neither. And all we have is a table of values. And then if it appears to be exponential, we want to actually build the function that passes through the points. So, back up here when we made the table for linear and exponential, there is another thing that maybe would be worth mentioning. For the linear model, from one output to the next, I'm just adding the same number over and over again. Specifically, I'm adding the slope value. I'm adding 2 in this example. Because it's linear, the slope between the points is the same. Whereas in the exponential, rather than adding, now a different relationship is happening. Can you tell what the relationship is between these outputs in this table? Rather than adding 2, it looks like we're actually timesing by 2, right? A half times 2 should be 1. 1 times 2 would be 2. 2 times 2 would be 4. 4 times 2 would be 8. So if you have a table of data that's linear, you should be able to observe an addition from one output to the next. Whereas if your table of data has an exponential relationship, you should observe a multiplicative relationship between the outputs. So with that all being said, let's look at this question here and consider how the output values seem to be related. I'm just going to change my paper back to blank paper for us to work here. So what do you think is happening as we look at these values? We're going to ask ourselves, from 3 to 0.9, am I adding something or am I multiplying? If I was adding, technically it would be subtracting, right? I would be subtracting, I guess it would be 2.1, right? To get from 3 to 0.9, okay. If I am multiplying, 3 times something would need to give me 0.9. So the decimal may throw us off there a little bit, but we know 3 times 3 is 9. To get it to be 0.9, we would just times by 0.3. So we could either subtract 2.1 or times by 0.3. That's from the first output to the second. Let's explore the relationship now from the second output to the third. So from 0.9 to 0.27, again, if we were looking at it from an additive kind of relationship, we would be subtracting really. And how much would we be subtracting? So to get from 0.9 to 0.27, that'd be what, 0.63, I think? So we could either subtract 0.63, or if we think about it from a multiplication perspective, 0.9 times what number would give us 0.27? Again, let's kind of ignore the decimals for half a second. I'm thinking about 9 times what is 27. So 9 times what is 27? Well, 9 times 3 is 27, right? So we know a 3 is involved. In terms of the decimal places, if I have a 0.9 and I want to times it by some value with 3 involved to get 0.27, I'm going to need it to be a 0.3, right? Because then we would have the 2 decimal places. So 0.9 times 0.3 would be 0.27. So we could either subtract 0.63 or times by 0.3. So at this point, you may already feel clear enough from that little discussion what the relationship is for this set of data. If it was linear, like we saw in the example up above, I would need to be adding or subtracting the same number to get from one output to the next. Again, assuming there's an equal amount of change in the inputs. So in this data table, they're not trying to mess with us in that way. You can see I'm just going from 1 to 2, from 2 to 3, from 3 to 4, right? So I don't need to worry like I'm going from 1 to 2 and then 2 to 20. They're not trying to trick us in that way. So for it to be linear again, these values that I'm writing that I'm subtracting would have to be the same. But negative 0.21 and negative 0.63 are not the same. For it to be exponential, we should be able to show that we're always timesing by the same value like we saw in this example, where we were always timesing by 2. So far, we found from the first output to the second and from the second to the third, timesing by 0.3 was working. So just to really convince you, let's check out this relationship between 0.27 and 0.081. Again, I think we've ruled out linear because we're not subtracting the same amount from one output to the next. But from a multiplication standpoint, is it true that 0.27 times this 0.3 would give us 0.081? And it looks like it, right? 27 times 3 is definitely 81. And then we have total of 3 decimal places, which we see in the 0.081 as well. So that same relationship of timesing by 0.3 again applies. So this data set definitely looks to be exponential. So we've answered the first question. Is it linear, exponential, or neither? And neither would mean you couldn't find a multiplicative or additive relationship, but we did find it to be exponential. So if it's exponential, which it is, we got to actually find a function, the equation of a function that would have this table of data. Cool, so let's talk about a couple options for actually building the function now. I'm going to make a little bit more space for that discussion. We've learned a bit about the general form for exponentials. We know they look like y equals a b to the x. And we know, let's see, a couple things. If you plug in 0 for x, the output will be a, right? That would be true. So that would be the y-intercept. So in this model, the table that we see doesn't include an input of 0. But if we just determine together that we're simply timesing by 0.3 to get from one output to the next, doesn't that imply that if I moved to the left by 1, I would simply divide by that same value rather than times by it? So if I wanted to make a row for 0, I'm just kind of adding onto the table here. So 0 would be 1 to the left of 1. I would just have to take 3 and divide it by 0.3. And what is 3 divided by 0.3? That should give us 3 divided by 3 would be 1, but it's divided by 0.3, so that actually gives us an extra 0, so 10. So that's one way that I actually like to use to figure out the a value for my function. So if our model needs to have that same structure of ab to the x, where a is the output for the y-intercept, we just found in the table that when x is 0, y is 10. So that value of 10 becomes our a value in this ab to the x model. Cool. So again, I'll give another option after this, but this is kind of more an observation method for those of you who like to look at patterns and characteristics. Now b, let's float back up to our example from earlier. B is actually just the number that you're multiplying by from one output to the next. So in this example where I gave us y equals 2 to the power of x, in this example, the a value is 1 and the b value is 2. So I'm simply timesing by that b value of 2 to get from one output to the next. We've already talked then about the b value for this model. It's that 0.3 that we've been discussing. So the b value in our model will be 0.3. And that will be raised to the power of x. So again, we're kind of slowly but surely filling in our model. So that's kind of my preference for building the equation, is walking through it like that. But I'd love to give you all another way to come up with the function as well. So this one is more by observation, right? This 10 is the value when you plug in 0 for x, what you would get back. This 0.3 is the change from one term to the next. And just to circle back to something we said earlier in this unit, because the b value is less than 1, it's going to decay. And that's true in our table. These values are getting smaller as the inputs get larger. So it's an exponential decay kind of situation. All right, if you're still with me, I will share one last way to come up with the equation. So let me start from scratch. And we'll come up with that same equation another way. And maybe to be more fun, let's keep this over here, and we know we better get that same answer when we do this another way. Let me see if I can make this a little bit more beautiful real quick. Okay, so this is our goal. And with this other way, we're going to use that same structure of y equals ab to the x. And we're going to steal two data sets from our table here. So let's grab 1, 3. And if we apply the point 1, 3 to this y equals ab to the x model, I would get 3 equals ab to the first. Let's grab another point from our set of data. Let's grab 2, 0.9. And let's plug that in. So plug in the 0.9 for the y, plug in the 2 for the x. And then all we're going to do is divide these two equations. So it's a little weird to think about dividing equations. So I'll write it out again. We're going to divide the 0.9 by the 3 on the left. We're going to divide the ab squared by the ab to the first on the right. So we're just basically sticking a big division bar between them. The reason why this works out well is you guys can see on the right hand side, the a's cancel out. And then if I have b squared divided by b to the first, that's going to simplify to just b, right? And here's just a visual reminder that b squared being b times b shows us that we can cancel out one of the b's on the bottom. So this strategy allows us to quickly find the value of b. 0.9 divided by 3 is going to be that 0.3 that we've talked about a little bit with our other process. And then in this method, since we found the b value, I can update our model. So I can just say at this point, based on the b we just found, y equals a times 0.3 to the x. And then I can just use any ordered pair from the data set. Maybe I'll use 1, 3 to solve for a. So I'll choose that 0.13 and I'll plug it in to solve for a. So I'll plug in 3 for y. We already know b is 0.3. I'm plugging in 1 for x. So 0.3 to the first is just 0.3. So a times 0.3 is 0.3a. I'm going to divide both sides of that equation by 0.3. So 3 divided by 0.3 is 10, and that leaves a by itself. So using this method, I believe you'll agree we arrive at the same conclusion, which is y equals 10 times 0.3 to the power of x. So that's just an alternate method, or maybe you're working on a problem where it's hard to do it by that first method where we are doing more observation, so you feel a little bit more concrete when you do it the second way. So hopefully that helps. I know this was a longer video, but hopefully talking through those ideas, first about that difference between linear and exponential, and then seeing it in an example, hopefully that all helped.